Okay. And let me try this. Okay, this is annoying. Okay, it's here. Okay. And yeah, let's have a quick start on our chapter 4. Okay, so sorry for very late. So let's try to go quickly on 4.1. I think our yeah, sorry for being late. And but I think our progression should be okay. But anyway, so we start with a new thing. So we finished chapter 3 talking about linear spaces. And now we are going to talk about more things about linear algebra. And the next thing, so now we have the linear spaces. The next thing we want to talk about are those transformations. Okay, so what a linear transform is mapping between linear spaces. Okay, so basically, on chapter 4, we want to study mapping between linear spaces. So we have define all those vector space V in chapter 3. They specify closure and all those axioms. And they can do linear operation on that, and they have a linear independence, etc. And now we want to see how can we map from one vector space to another vector space. But we want to keep linearity. And what we mean by keeping linearity is we want to keep this linear structure. Means that, so if you have two vectors, v1 and v2, and you want to map them, so v1 and v2 are in this first vector space V, and you want to use this mapping to map them to something inside W, and you want to keep the linear structure of the vector space V. So you know vector space V has this linear structure. You can do linear combination on V, and W is also a linear space. It has a linear structure. You can do linear combination. So you want these two linear combination structure to be matched. So mapping is a linear transformation if the mapping respect the linear structure of V of W, V and W. So if you have a linear combination on V, then you will have the corresponding linear combination. When you map to W, you will keep the corresponding linear combination. So you have alpha V1 plus beta V2. You will get map to alpha and the map of V1, and beta and the map of V2. Okay, so this is for every alpha beta and every V1 V2. Okay. And another way to write this is, okay, so we know linear combination is basically two things. You can do addition and scalar multiplication. So you can also write this rule as two separate rules. So you can say this linear map will respect the addition. So addition map of the addition is the addition of the map, and also it respects the scalar multiplication. So you do scalar multiplication on your input, then you have a scalar multiplication on your output of this map. Okay. So yeah, so you can write those two conditions or this one condition. They are equivalent, pretty easy to show. Okay. And yeah, so this is called a linear transformation. So mapping from one vector space to another vector space. If we preserve this linear property, then it's called a linear transformation. And a few more notations. So this is actually a more general notation. This is a notation for any mapping in mathematics, but here we use it to denote the mapping that's a linear map. So we write this L, and the comma means that we are not describing this mapping L, and it's from V to W. So it's just a mapping from V to W, mapping from V and map to W. Yeah, so this is the input space and the output space of your map L. Okay. And yeah, and one more notation. So if v and w are the same space, a lot of time you are just transforming vectors inside your space V. Then you have a mapping from V to V. Then this is called a linear operator. Yeah, V is a linear operator. And okay, so we have a linear operator. So let's see some example. Very easy linear operator is so you do some linear operation on vectors on vectors on inner space. For example, your L of x, you map from so you have a linear operator on R2, so you map from R2 to R2. And the first linear operator is just you multiply your vector by 3. So L of x becomes 3 of x. So we have a very geometric interpretation. You have whatever vector, you increase the length by 3 here. Okay. And so we can check the two linear properties satisfied. So L of alpha x equal to 3 times alpha x, and because multiplying by alpha and multiplying by 3 interchange, so this is equal to alpha times L of x. Okay. So basically, we need to check this equation and this equation, and we check this first. And so if we have two vectors x and y, and we want to see what's L of x and y, that's 3 times x and y, and we see that's 3x plus plus 3y, and exactly L of x plus L of y. Okay. So L is a linear transform or a linear operator. Okay. And we can have other example. Okay. And this example is, well, this is not one-to-one anymore. So we have L of x equal to x1, e1. If your x is x2, x1, and x2, so basically we throw away the we throw away the second coordinate, and so L of x is just x1, e1. Okay. And yeah, so we have so once again, so now we use the checking that we just check both conditions together. So we have x and y, and we want to see what's L of alpha x plus beta y. Okay. And you can write down the, and so you can write down alpha x plus beta y. So x is on x1, x2, y is on y1, y2, and so alpha x plus beta y is this alpha x1 plus beta y1, alpha x2 plus beta y2, and you put this arrow on it. You change the second coordinate to 0, and once again you see this is alpha arrow plus beta y. So arrow is once again a linear transformation, and this is in R2. So we have a geometric interpretation. So we have whatever vector x1, x2 here. And you get rid of the second coordinate, so this is a projection onto the first coordinate here. Okay, so we haven't defined projection. Projection we will define more rigorously later, but we can feel this R2 projection as what we learned in high school. So you project this vector onto this x-axis, x1 axis. So you just left with this vector with length x1 here, and nothing on x2. Okay, so this is also a linear transformation. Okay, and yeah, we have a more complicated example here. So more complicated example in R2. So x equal to x1, x2, and L equal to x1 and minus x2. So let's to see the geometric first. So basically, what this do is we do a reflection around x1 axis. So we have x1, x2 here, and we become x1 minus x2. So x2 become minus x2 here. So you do reflection around x1 axis, or you put a minus sign on the x2 coordinate. Once again, you check L on alpha plus beta, alpha x plus beta y, and you get a minus sign here, but putting a minus sign is linear here. So you see this is also equal to alpha Lx plus beta Ly. Yeah, so you can go from here, and you have xy, so you can just do this calculation, get this thing, and you can go also other way around here, and you see you also get this thing. Okay, so alpha x1 plus beta y1, and minus alpha x2 plus beta y2. So L is once again a linear operator. And yeah, now we have a more complicated example. So next example in R2, L equal to minus x2 and x1 when x is x1, x2. And now this is less easy to see, but it also has a nice geometric interpretation. So what is x1 to x2 go to minus x2 x1 is this rotation by 90 degrees. So you have x1 x2 here, and you see this is x1, and it was x2. Oh, sorry, this is x1, and this height is now x1, and this is x2 here, and now this is minus x2 here. Okay. And yeah, you can work out beam moments, and you see that this is the rotation by 90 degrees. Okay. And rotation is also linear, because if you can kind of feel geometric here. If your vector length is increased by some number, then your rotation is also going to this. You can do rotation first and increase by number, or you can do increase by some factor alpha and the rotation. It will give you the same result. Okay. And similarly, you can have addition of a two thing and then rotation. Then that will be same as you do rotation of a two thing, then the addition. Okay. Geometrically, you can kind of feel it's a linear operation, and then you can work out the matrix algebra. You see that the arrow of alpha x plus beta y equal to this minus alpha x2 plus beta y2, and alpha x1 plus beta y1, and you work the other way. You have alpha LX plus beta LY, you will get the same thing. Okay, so yeah, you can also check algebraically that this is a linear transformation. Okay, so I think that or for example of R2, there are more or very geometric examples. So you have this rotation, that's a linear, and this reflection, that's linear, and also projection, that's linear, and this is just a linear extension. Is this is multiplied by a constant is linear. Okay, and yeah, let's see more example. Okay, so we have a more complicated example. We can have a linear transformation. So now it's not linear operation because we are changing the input and output space. We can change it from Rn to Rm, both on n and m. Okay, so first we have a very easy example. So we have R2 to R1. So we have some L of x just equal to x1 plus x2 if our input vector is x1, x2. And yeah, you can check that L of alpha x plus beta y is just adding together all the alpha x plus beta y, and that equal to alpha LX plus beta LY. It's also a linear operation. And finally, we see something that's not linear. So if we define some mapping n of x equal to x1 squared plus x2 squared times square root 2. So this is taking the length of your R2 vector. And this taking length of R2 vector, well, it turns out that it's not linear. So you can check two things. It satisfies the linearity with respect to this scalar multiplication. So if you have alpha times, oh sorry, it's sorry, it doesn't respect the it doesn't even wrong. So it doesn't even respect the the scalar multiplication on linearity, the scalar multiplication part of the linearity. So you might think that you multiply by alpha, your vector length will increase by alpha, but it's a bit tricky. That's when, because sometimes alpha can be less than 0. Okay, so if you multiply your scalar by you multiply your vector by alpha, then the length of a vector is actually increased by this absolute value of alpha. Okay, but if you you want you want your mapping to be increased by a factor of alpha, and alpha will not equal to absolute value of alpha when alpha is less than 0. Okay, so m is another linear transformation. Okay, and I think it's even easier to check if you have when you have addition is also not satisfied. Okay, and it's very easy to see. Basically, almost any example of x and y will give you n of x don't equal to n of x plus y. Okay, and yeah, this is this example, and Next example, we have L equal to, we have L from R2 to R3, and it's defined by this quite arbitrary function. So L of x equal to x2, x1, x1 plus x2. So basically, you see that in any coordinate is a linear combination of input of L. Okay. And once again, you can check these two things, or you can just check them together. You see that L of alpha x, because everything is a linear combination of input, then this linear combination works well with scalar multiplication and addition here. Okay. And I guess let's try to go over 1 minute. And here we see that this is the next example. So this is a thing that we'll do a lot, and we'll do more in 4.2. That is, we are going to express a linear, this linear transformation as a matrix. Okay, you see that here every coordinate is a linear combination of the input coordinate. So we can write down this linear transformation as a matrix. We have A equal to this 0, 1, 1, 0, 1, 1 matrix. Then L of x is just A multiplied on your input vector x1, x2. Okay, and yeah, this is a general thing. So we have one-to-one correspondence between transformation from Rn to Rn, any Euclidean space linear transformation. So if you have a matrix, you can write down linear transformation, and in 4.2, we'll see that whenever you have a linear transformation, it can be written down as a matrix. Okay, and yeah, that's all I have time to talk about today, and we'll see you on next Monday. And also, hopefully, you will get the exam graded on next Monday, and we'll also do the exam, the midterm overview on next Monday, hopefully. Okay, and yeah, so see you on next Monday.